Alright, we have many different examples about it. The gene and disease network, even though they are related, and we can create a bipartite graph. So sometimes it gives you more visuals and more intuitions between the relationship between the genome and phenome. I don't know what that means. So please let me know when you are from biology, right? Many people, right, already know better than me. Human disease. You can create that in bipartite graph, right? From the observation. This is ingredient flavor bipartite network, and by looking at the food, so we have some ingredient information, right? Shrimp, garlic, tomato, but we see the flavor components in the ingredients, and we can create the bipartite graph. And by looking at this, we can create flavor network. So the bipartite graph could be, sometimes it is more useful. And when we started from this bipartite graph, we can convert the graph to some flavor network information. So in the bipartite graph, we don't know the relationship between the ingredients, right? But by looking at the flavor components, and when they have some common components between the ingredients, and we can create some edge, and we can decide the strongness between the ingredients, and we can create this sort of the visual, right? All right. Now we have another concept, path. So what is path? Path is a sequence of nodes in which each node is adjacent to the next one, right? Just go the path is path, right? But mathematically represent this sequence, something like this, right? Sequence of nodes. This is a mathematical notations, right? Another notation for the path is the sequence of edges, right? 0 to 1, 1 to 2, 2 to 3, right? We have two different ways. In the directed network, the path can follow only the direction of an arrow, right? It is not even sometimes the direction is given something like this, and it is not possible to go to this direction. So you need to stop here, or go to another direction. So by having this, the concept of the paths, now we can define the distance. So this is another concept, and very important concept in a graph data. So what is distance? So sometimes you call, the distance is a very long and short, and we need to have some criteria, right? And how to quantify the distance. How would you quantify the distance, right? Maybe we use shortest path between A and B to say B is very far from B, A is very far from B, by considering the shortest path, right? In geodesic path, it depends the coordinate information, right, between two nodes. in directed graphs, we still need to follow the direction, right? So we can also talk about the number of paths between the two nodes. If the length is equal to 1, if there is link, we can put the information in the adjacency, right? Actually, this is from the pure definition of the adjacency, right? Adjacency matrix. When the length equals to 2, right? How would you represent that information from adjacency? So 2 means here A, B, C. The distance between A and C is here 2, right? 1 and 2, right? So to represent this one using the adjacency matrix, we'll see two different adjacencies. So from I to J, we look at there is a varied K between I and J. So in this case, oh, it's gone. I, K, J. When we look at IK 1 and KJ is 1, when we multiply this information, we see they are connected to each other. And by looking at the value, right? Otherwise, it will be 0. But we need to see what the K is then, right? That's why we iterate every K in the node set, right? And eventually, to see if there is a path between the length 2 between I and J, we just multiply the matrix A and see the ith and jth position, right? So A square means A is multiplied by A. This is just matrix product, right? Nothing special. So matrix product, and see the location, right? Ith, jth, looking at the number. Could be 1. Oh, we have just one path between I and J, right? So to compute the number of paths with length n, we need to multiply the adjacency n times. But you need to remember that this is a very heavy computation. Matrix multiplication is computationally very heavy. And you will have so many memory you will use, So n is more than 2, it will be very, very dense, regardless of the sparsity of the original adjacency. So it will quickly become very dense. So to compute this information, you need to think about some distributed computation for this, or some another approximation. All right. Take some rest even when you're tired. But I need to keep going. Oh. So, finding distances. You can use the BFS, right? So to see the distance between 0 to 4. Start with the 0. See the nearby neighbors and put them in a queue. And to see the distances, right? I would like to say the nature of the BFS corresponds to the distances between the source node, right? So now we came to the end, right? So here we another concept of the diameter. So we often refer to Dmax, the maximum distance between any pair of nodes in the graph, and average path length and distance for a connected graph. So this is computed like this. On an interacted case, computed something like this. So it is connected. So this is a directed case. So we put the 2 in here. So for the path, so we talked about many different criteria to generate the path, right? To define the path. Maybe shorten the path, just considers the distance, right? Try to minimize. So we have, by having the traversal in the graph from the source, and we just build the shortest path information toward all the possible nodes, right? This is one criteria for computing the distance or defining the path. And diameter and longest path, right? And average path length is just average of all the shortest path for all pairs of nodes. So averaged all the path lengths. And you can define the cycle, right? This is the cycle. And self-avoiding path means it does not interact itself. So when it departs from a node, their node, it doesn't come back to the position, right? Cycle come back again, right? So Aurelian path is the path traverses each link exactly once. It considers this edge and traverse all the edges in here, something like this, right? Hamiltonian and path that visits each node exactly one. So they are NP-hard problem, right? So connectivity. So it is to define, usually to define the largest component. Sometimes we call largest connected component or giant connected component. So connected graph, so any two vertices can be joined by path, right? So they are connected, right? The disjoint graph is made up by two or more connected components. So it has two connected components. The rest is called isolate. So here we have new concept of the bridge. So we have so many different definitions of the bridge. So in the traditional graph theory, the bridge means if we erase it, the graph becomes disconnected, right? So this is called the bridge. This is the bridge, right? So connectivity of undirected graphs. So they usually could be visualized something like this, right? We have two different connected components, right? A red one and blue one. So when you see this, it looks like a blocks, two blocks, right? So when you observe this sort of the presentation, I would say, and you have two different connected components. This is also called the block structure. And you have some bridge information, something like this, right? So when you plot this to the visualization, like the previously in the grayscale, and we put black value for the 1 and 0 value for the white, and you have something like this. That's why it is called the block structure. So when it is dense, it will be something like this, right? It is called squared block. It is also called never mind. So block. So connectivity of directed graphs. So we have strongly connected directed graphs. It has path from each node to the every other node, and vice versa. That's why it is called strongly connected, right? What is a strongly connected node? Has a path to the everybody. In this example, maybe has a path to everybody, right? A and D and B, C, E, G, and F. Oh yeah, E is strongly connected graph. So weakly connected directed graph means that it is connected if we disregard the edge direction. So yeah, this is weak. Right, just read the sentences and very straightforward, right? So maybe you can just come back when you read the graph related paper. They just, without explaining the details about the terminology, just directly say, oh, they are strongly connected directed graph. And we need to come back here. Oh yeah, what was the meaning of the strongly connected graph? And what is connectivity? What is block data structure? And largest component, right? Just come back here. But they all are very intuitive, and hopefully you remember pretty well. So it is to find the connected components, and often we use the BFS, and just follow the BFS, we'll see the connected component. So just read the sentences here and think about it. In the last concept in this class is clustering coefficient. So we have two different clustering coefficient: local clustering coefficient and global clustering coefficient. For the local clustering coefficient is to compute what fraction of your neighbors are connected. It is to compute the fraction. So in other words, it has the exact target, I mean the node I. So considering the node I and their neighbor, we'll see how many the neighbors are actually connected. In this case, this is the perfect, I would say, just the largest score. So when you see the i's neighbor, they all connected, right? So think about this one. It is connected to here, here, here. What about this? Connected here, 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 right? So it is count. So numerator, look at the numerator. So Eij is from the neighbor of the node I, right? We have several neighbors, right? From I. Yeah, I'm sorry. So we'll see the in I is from the connected neighbor, right? So in this case, the blue, all the blue, right? We have 4 blues, right? So we have 4 different blues. So we see their combination, right? We see the combination. We count the possible edges between their neighbors, right? We just count number of varied neighbors, varied edges between the neighbors, right? It is to count this. And the numerator is to represent the possible edges. That's why it is called the fraction. What fraction of your neighbors are connected, right? So we see 0 value, they're not connected to each other, right? And we have 2 different coefficients for directed neighbors and undirected neighbor. So because it has different possible the edges between neighbors for the numerator, right? Remember the 2 over k minus 1, right? So it goes to this here. All right. In the case of global, considering all nodes, we count number of closed triplet. Triplet means, come on. In the previous example, when the neighbors are connected, actually it looks like, so here the neighbors connected, and actually it formulates the triplet, right? Because the blues are from actually node I. When they are connected, we can observe the triplet, the triangle, right? We just count closed triplet. Another explanation, all the possible number of the closed triplet, and it is divided by number of all triplets possible, right? You just compute like this, right? When C is 0, when the denominator is 0, so for the exception case. All right, so we have talked about many different concepts, right? So whenever we need, we will come back here again. Just this is the second class, so we need to slightly settle down in this build. We see get a sense of the basics, and so feel more comfortable, right? We will directly jump into some more machine learnings in the next class. So any question about this class, please let me know. So we'll prepare a Q&A time pretty soon. And in the meantime, if you have any question, please let me know. Thank you for your attention and see you next time. Have a great week and great weekend. Bye bye.